Ah, welcome back. I hope you all were able to enjoy your spring break, however you were able to enjoy it. We are now in the final stretch of this year, and I was looking at the things that I want us to do, and I'm going to try to kind of cut out some of the fat. As you can see, I do want you to know about the six level machines. I do want you to know about things like momentum. So we're going to kind of get probably not in depth as to we were if we were in school, but you're definitely going to at least be familiar with a lot of the concepts. I'm probably going to cut out things like sine and cosine that make it unnecessarily mathematical. Try to stick a little bit more to just the physics itself. So the next simple machine that I really want to get to is the pulley. But I realize we can't study pulleys unless we have a good concept about what the word tension means. So tension is going to be the focus of today's lesson. Tension is a force. It is a force that is exerted throughout a rope or a string or any object that kind of simulates a rope or a string. So I have two pictures here. I have a weight that is hanging by these hooks to a ceiling. So technically, what is holding the weight up? Well, it's on a string, but the string is pulling it because of something called tension. People playing tug of war right here, again, they are pulling on the rope, but they're not moving because of the tension in the rope. They pulling the rope is pulling them back, and that force that they're pushing into the rope is called a tension. We're going to get more into that today. So tension is simply defined as a force in a rope or a string. That is an overly simplistic definition, but I think it's a good way to kind of think about it right now. So every single time when I would say hold it taut, what I was saying was hold it with a great deal of tension. I want there to be so much force in the string that the string or the rope or the tape measure doesn't have any ability to move. So I was just Googling images and I found two pictures here. I'm going to call this picture 1 and I'm going to call this picture 2. I want you to think of tension in the way that it exists in the world. I say rope or string. It doesn't have to be rope or string. Tension can be in a power cord for a phone, for example. Tension could exist in a dog leash. Tension could exist in when you tow something, there's tension in the hook between the car and what you're towing. So tension kind of exists in a lot of different ways. So I say rope or string, I kind of mean that in a generic way. So if I look at this, if I look at picture 2, that cell phone right there is being pulled down by gravity. The tension in the charger is holding it up. So gravity pulls it down, F of G, and then the tension, F of T, holds it up. And that's why it's not going anywhere. The forces equal and opposite, they cancel out. That it must be a really good plug in a phone because most of the times the plug of a phone is not capable of supporting the weight of the phone. So it's probably a new phone right there, I would imagine. But when I look at picture 1 and I see that the phone is in the cord is wrapped around, I want you to know that yes, gravity is still pulling it down, F of G, but the weight of the phone is now distributed on these sides of the wire together. So what happens is you actually have less tension in the wire because what happens is you distribute the force to the different sides. If I look at it like that, if I think about it as a free body diagram, there's tension on this side, there's tension on this side, they have to add up and cancel this. So these two tensions here and here have to cancel this, whereas I only had one tension over here to cancel this. So if your phone doesn't, if it's older and the cord doesn't want to stay in, and you want to kind of wrap it like this. The more times you can wrap it, the less tension you'll have in your cord, and the easier it is to be a move, and the easier it is to keep the plug in. So this is an interesting way to kind of keep your phone plugged in if you don't want it touching a surface. Try it out if you want it at home. So again, tension is just can be applied in very different ways. So like if anything that is a straight line that is getting pulled has tension. So if you are walking with a dumbbell in your arm, you could say there's tension in your arms, okay? You may, in biology studies, they're called surface tension. When the water was flat, there was something called surface tension. It was a force that didn't want things to go into the water. Interestingly enough, if the water's not flat, there's really not much surface tension. So I've said this before, but if you fall a great distance into flat water, it hurts. If you do a belly flop into a pool, it hurts. The flat water slams against your body. But what happened was, let's just say you had a handful of pebbles and you were falling into the water. If you threw the pebbles into the water, and what the pebbles would do is they would break up the surface of the water, it would lower the surface tension of the water and therefore lower the resistance the water would have to your body coming in. It's another way of lowering the tension in the water. And towing, I said, is another great example of tension. So tension is anything in a straight object where force is applied, typically a rope or a string. So that is tension. Tension is known as the F of T in free body diagrams. You saw me write that, but I want you to know. So we had F of G, we had F of N, we had F of FR, we had F of P. I told you all these forces existed, and I wanted you to know that there would be many other forces. So here is a new force. We never did this force last year. It is a brand new force, but forces are forces nonetheless. A force is a force, of course. Forces go into free body diagrams, and you know how that works. So if you think about it, all of these people in this first picture, they're pulling the rope. No one is pulling each other. You cannot say that this person is pulling this person. They are not touching. This person pulls the rope, and then that is forcing this person this way, and that's why he has to lean back to cancel out that force to stay still. They are trying to cancel the tension in the rope. What I did want to get to this year before all this was we could have tension in multiple directions. So if you look at the picture in the bottom here, people are pulling this rope in multiple directions. This is actually a football training equipment I found where all 4 people are pulling in a different direction, and they are competing against each other to go ahead and reach their goals. And essentially you're all creating more and more tension in the rope, and the more tension that's in the rope is harder for you to move, so you have to pull a little bit harder, and it's a good workout technique in that way. Okay, so there's going to be math to this, of course. Let's look at this situation. I have 2 boxes hanging from a ceiling. I have M1, and M1 is 5 kilograms. Okay, 5 kg. Very good. And I have M2, which is 10 kg. All right. They are just hanging still from the ceiling. They are not moving. Since they are not moving, we could go ahead and say that the acceleration is 0. They're not moving. So if we know that the acceleration for each of these boxes is 0, we know that the net force of each box is 0. Okay. They're not moving, so all the forces have to cancel out. But let's just look at the picture. Which rope do you think is going to have more tension, more force in it? T1 or T2? Which one is going to have more tension? T1 is going to have more tension. Why? technically speaking, T1 is holding up both weights. T2 is only holding up one weight. Because T1 is holding up both the weights, technically speaking, because if T1 wasn't here, both boxes would fall down. But if T2 wasn't there, then just box 1 would be there. So let's go ahead and see if this is true. Let's do this by drawing a free body diagram of each individual box. All right, so I'm going to start with M2. M2 has a mass of 10 kilograms. Because this is being held vertically, I know that the gravity is pulling on it. Gravity is going to be 9.8 times the mass, or 98. 98 newtons is going down. The only other force acting on this is the tension force. The only other force acting on this is the tension force. No other forces are acting on it. So I know that the net force for this box is 0 because it's not moving. It's not accelerating. So that means that the F of t has to be 98 as well. So it can have its two forces canceled out. Do you see how this is a free body diagram for M2? Okay. Now, M1 is going to be a little bit different. M1 is going to have more forces acting on it. What do you mean? Well, M1 is going to have the tension going up. It's going to have the gravity. And it's going to have the tension. So I'm going to label these. I'm going to call that T2. And I'm going to call this T1. And I'm going to call this F of G. M1 has both tensions acting on it. The T2 is pulling the M1 down, and the T1 is pulling the M1 up. Both tensions are acting on it. Okay? That's the thing about a rope. That's the whole point. If you just pull it and there's no tension in it, the rope moves. But when tension occurs, then that rope is pulling objects at either side of it towards the middle. So this rope right here is technically pulling the M2 up, and it's pulling the M1 down. That's the essence of tension. It's pulling both ways. Okay? And if ever it can't happen, it'll snap, it'll pop off. So, for example, if you are pulling your phone to you and it's plugged into the charger, you're pulling the cable of the charger. As long as that tension doesn't get too high, as long as you don't pull it too fast, create too much acceleration, potentially the phone could stay attached to it. I've used this in terms of inertia, but it can be explained better through forces of tension. As long as there isn't too much tension in that rope, it won't snap out. Okay, so M1 has multiple forces on it. Gravity pulls on everything. I hope we know that. That's not crazy there. But we know that the tension is going to be going up and the tension is going to be going down as well. T1 up, T2 down. So M1 has a mass of 5 kg. 5 kg. 5 times 9.8 is, of course, 49. T2. We already solved for T2. T2 was going to be the same thing this was T2. So what we're saying is, if this is 98 going up, then it's also going to be 98 going down. It's the same force. It's just pulling in equal and opposite directions. That's the essence of tension. It pulls the same amount in equal and opposite directions. So because the T2 is pulling up on the M2 98, the T2 has to be pulling down on the M1 98. But we know that the T1 has to cancel all of the down forces. We know that it's not moving, so the net force has to be 0. So if I add these up, I get the T1 of 147 newtons. That is the T1. Now let's look back. We said in the beginning that T1 was going to have more tension because it was supporting both weights. Mathematically, that's what we got. It's consistent. So, when you have a situation like this, start from the bottom and work your way up. If you know that the net force is 0, you know what all the forces have to add up to be. Okay. Now this one gets a little bit more complicated. This time we are pulling boxes horizontally to the left. It says M1 is 3 kg. It says M2 is 5 kg. It says M3 is 4 kg. And the force is 35 newtons. Awesome. So, I want to draw the free body diagrams of each box. Just like before, we know that they're all going to move together. If you're pulling to the left here, all these boxes are going to move at the same speed. No box, it's not like I pull it this way and then box 3 slams into box 2. That's not how it works. If I stopped moving, then they might continue moving and hit. But if I'm just pulling it, they're all going to move evenly. So, you could think about this as like a toy. I like to think about this as like a toy train. You know, each of these would be a train car. If you pull it, they all move together. Okay. What we're going to do is we have to figure out what the acceleration of the whole system is. So I know that we're not going to deal with friction in this, so let's just assume there's no friction. I know that acceleration equals net force divided by mass. Well, I know the only force is horizontal 35. I know the gravity and the normal, they're all going to cancel out. I understand all of that. So this is what I can do. I can even just draw them in. We know how to do gravity and normal. I'm not drawing these to scale in any way whatsoever. But I know that these are going to be the gravities, F of G and F of N. We know how to do that. That's not hard. So let's look. Let's look at all of these individually. In order to get the net force, we know that the gravity and the normal are going to cancel out. We only have this horizontal force of 35. How much mass is that 35 going to move? Well, if I'm pulling it 35 to the left, it's moving all 3 masses. So what you're going to do is you're going to add all the masses up individually, because that pull is distributed to all of the masses. So the acceleration is simply going to be the force of the pull divided by the sum of all the masses. Let's just call it 2.92. So I know that every box individually has an acceleration of 2.92 meters per second squared to the left. In the last problem, I knew it was 0. But because it's moving in this problem, I have to do this extra step. I take the pull and I divide it by all of the masses together. That's the key here. Now that I know that, I can now draw the individual free body diagrams. When you do this, start with the one all the way at the end. Okay, so we're going to start with M3. So here's M3. All right, and M3 is a 4 kilogram box. I want to draw the individual FBDs. All right, and the only force acting on it is this. Horizontally, we have gravity, and that's going to be 39.2. And because gravity is pulling it down 39.2, we know the normal is going to be holding it up 39.2. But if I know it is accelerating, if I know that the acceleration is to the left, 2.92, how can I get this arrow? Oh, acceleration, mass, this is really the net force. Net force equals mass times acceleration. So if I do 4 times 2.92, I get that the tension here is 11.68. Oh, okay. So the tension there is 11.68. So that means that this tension is really TB. It's pulling left 11.68, but let's think about it in terms of the whole system. What we have here is we have a 5 kilogram mass here. If that rope is pulling left 11.68 on the 4 kilogram box, it must also be pulling right 11.68 on the 5 kilogram box. Tension pulls equal and opposite. Tension pulls equal and opposite. So if it's pulling the 4 kilogram box to the left 11.68, it's pulling the 5 kilogram box right 11.68. So I want to go ahead and I can do the gravity and the normal force. So that's going to be 49. Okay, you know how to do that. That's actually not that important. Okay, but how am I going to get this? Okay, what is the acceleration of this 5 kilogram box? The acceleration of this 5 kilogram box is 2.92. All of these boxes have the same acceleration. So I'm going to do 5 times 2.92. All right, so I type that in 5 times 2.92, and I get 14.6. So that is the net force. However, do not put that in as the arrow. That is the net force. That is what I get when I subtract these two arrows. So what we're saying is that this arrow has to be 14.6 bigger than this arrow. So what I'm doing is I'm going to get 11.68 add 14.6. So I know that this has to be 26.28. Wait a minute, Pizzuto, you just lost me. All right, okay. I hear you. What I'm saying here is I have two horizontal arrows. They have to combine and give me a net force of 14.6. I know if this one is going right 11.6. The only way that these two horizontal arrows are going to combine to give me 14.6 is that if this was going left 26.28. We knew it had to be, the left had to be bigger because technically our acceleration is to the left, which makes it negative. The negative or the left side arrow had to be bigger. Cool. So now we have the last box, the 3 kilogram box. All right, 3 kilograms. I hope we understand where that came from. Gravity and normal cancel out. They need to be drawn because they are part of the free body diagram. So if we know that the tension on the 5 kilogram box is pulling left 26.28, that means the tension pulling on the 3 kilogram box right is also got to be 26.28. And we're going to do the exact same situation. So we need to figure out what the net force on this box is. The net force, because we want to get what this is. The net force is 3 times 2.92. I'm getting 8.76. So I know that this minus this has to equal this, because these are the arrows that cancel out. So I'm going to do 26.28 plus 8.76. Wait a minute. If I know that the net force here is 8.76, this number has to be 35.04. Wait, Bozzuto, that's really similar to the original force. Yeah, it's just a rounding error. It's the same number. We just proved that if you pull the 3 kilogram box to the left 35, it accelerates all of the boxes 2.92, and the tension between them is going to be 26.28 and 11.68. It all comes down to the free body diagram. So essentially, the only new thing we're doing here, it's kind of like a puzzle. You find one and you just keep working it out so that everything has the same acceleration. As long as you really understand how free body diagrams work, this should make sense. If not, follow the steps. Make sure that everything has the same acceleration. You get the acceleration. It's either going to be 0 if everything is still, or you're going to take the push and divide it by all the masses together. But then this is going to become the key. So, that's a lot. Not the easiest, not the hardest, but not the easiest thing that we've done. I expect there will probably be questions on this. So I want you to either email me, ask me. You can Google this. I did not invent this concept. Other websites exist. So if this explanation did not do it for you, feel free to Google these things. You will find these things on the internet. But they are absolutely part of an AP Physics course, and that is absolutely why we are going to learn how to do them, because once we get this concept down, we can then work on pulleys. So, we're back. We've 7 weeks or so left. We're going to make the most of it, and I am here to help. Please let me know how I can best do that.